Welcome to our first lesson of chapter 1. This is a short chapter. These lessons will not be long lessons. Most of this chapter will still be review for you. Some of it might be new depending on who your teachers were in the past and what they focused on. So generally, this stuff is stuff that in the US, when they teach calculus with our textbooks, and in some provinces, these things are not taught in Math 12 or Math 11 or whatnot. And so these are things that we need to go through just to make sure everybody's on the same page with notation before we start the actual new content. The previous review chapter we did was built separately because again, we need to make sure everyone's on the same page and has these basic skills before they start the course. It's almost like we have sort of two review chapters with little bits and pieces of new information. So everybody's going to have a different comfort level with the content in this section and this chapter. And some of it might be stuff that you haven't done in a fairly long time. My guess is the notation will probably be new for you, but the review of piecewise and absolute value stuff today should be reviewed. Okay. So just a reminder, a function is a special type of relation where each element in the domain is associated with only one element in the range. In other words, every input has at most one output. Okay. We use this notation, f of x, to represent a function, which we reviewed at the end of our review chapter 0. To determine if a graph represents a function, we used the vertical line test back in grade 10. This was where if you drew a vertical line anywhere on the graph, it should cross at most one time. So you can't just pick so that it works, it has to be true everywhere. To determine if an equation represents a function, we would check if for every x value or every input, there is only one y value or one output. A function can be represented in different ways by an equation, which we consider an algebraic method, a table, numerically, a graph, visually, or in words, verbally. The first set of elements of a relation is called a domain. These are your input or your x values. You should be comfortable with finding domain of functions if you are taking this course. The set of related second elements is called the range. These are your output or your y values. Same thing, you should know how to find ranges of functions or relations at this point. So for example, the area of a circle is represented by an algebraic form A equals pi r squared. And the question is, what would the sketch of the graph look like? So let's draw ourselves a nice little basic XY axis. Instead of X, we have R. Instead of Y, we have A. This would be a quadratic since we have R squared. And we know a quadratic looks like a parabola. This one has no transformations, no phase shifts or anything. Our vertex would be at 0, 0. However, it doesn't make sense to have a radius of 0, so we're going to put a hole here. This looks something like this. Okay? It's exponential. It's like half of a parabola. The other half doesn't make sense because it would not make sense to have negative r value. Okay? The question is this a function? Yes, it is. This is a function because for every r value, we only have one corresponding area that makes sense here. And if we drew vertical lines, each vertical line would only pass through our graph once. So yes, each r value has only one corresponding area or a value. Okay, a graph looks like a half parabola. With a hole at 0, 0. Okay, so what's our domain? Well, R has to be positive, right? And it can't equal 0 or we wouldn't have a circle in the first place. And same thing, our range would be our A values. A would also have to be positive, can't equal 0. If A was 0, that means we have no area, we have no circle, and we can't have a negative area of our circle. So the next thing that we're just going to go over is something called set builder and interval notation. So depending on who your teachers were, it will depend on if you've seen these notations before. The notations given here should be things that you are all comfortable with. These are X values, which would be domains of relations or functions. Set builder notation, you are going to use these funny little curly brackets that look like this. So some of you might have already seen these and you might already write your domain in this form. Okay. So set builder notation, what you do is you open your curly bracket and then you declare which variable you're going to use. So we're using the variable X here. So you're going to write an X and then you're going to write a line. This line is read as such that. So this is saying we're opening a set of variables X such that X is greater than or equal to 3. And then afterwards, we're also going to say that X is all real numbers. And it's not saying that our domain is all real numbers. We're saying that we have X is greater than or equal to 3. But once we get past that, we're going to include all X values past 3. The reason we do this is if you take more complex math, you might be looking at X values past 3 that are only integers, for example. So you might be only using the numbers 3, 4, 5, and none of the decimals in between. So we are basically just being very clear that once you get past 3, you are going to include every real number past 3, and then you're going to close your curly bracket. Interval notation. You're going to use sets of brackets, either round brackets or closed brackets or some combination of the two. Okay. And basically, the round bracket means you're going to include that value. The square bracket means you are not going to include that value. So you always start with the smallest number and build up to the biggest number. So our smallest number allowed here is a 3. We can include 3 because of the or equals to. So we're going to put a square bracket here. And this is going to go up to infinity. It goes forever, and you cannot include infinity. You can never reach there, so you're not going to include that. So this means that you include 3. This means that you do not include infinity. Okay. This is your smallest possible number. And this one here is your largest number. So you read this left to right. Includes 3 up to infinity, but does not include infinity. So we will try with this next one. So for set builder notation, you would open your curly bracket. We're still using the variable X here. We're going to declare that we will use X such that X is between -3 and 5 and including 5, or X is greater than 8. And other than that, X is all real numbers. Close your curly bracket. You can also separate these by an or here as well. Okay. Now, the interval notation is a little bit more tricky for this one because you have 2 chunks of your domain. So each chunk of your domain will be a separate set of brackets, and you're going to connect them with a U. Okay. So what this is going to look like is we're starting with -3 and we're going up to 5. We're not including the -3. We are including the 5. Or we can have greater than 8. So we start at 8 up to infinity, and we're not including either of those things. Okay. This means does not include. Okay. This one means includes 5. Okay. And this union sign, this U here, means union of. Okay. All right. So what this tells us is we have these two chunks of the domain that we must consider both of. Okay. If there was an upside down U, those of you who might take computer science might see that upside down U, or engineering, and that means intersection of, meaning those two domains would overlap. This U means union of, we're including these two parts of the domains together. Both of them must be included. You can't just have one or the other. All right. So it might help you to write down just some different pieces here that tell you what these mean. So, for example, the round brackets mean include, the square brackets mean do not include. So it might be helpful to write these down here. Okay, or put some examples there to include for yourself that might help you reference as you're doing your homework questions. And if you want, you can take a look online and see my version of some notes there. What, like, if x can't equal 5, for example, you're going to have from negative infinity up to 5, and then with a union of start at 5 again and go up to infinity. Okay, we're going to move on to piecewise functions. So if we want to sketch this graph, let's just go piece by piece. We'll maybe add some notation on, or some notches onto the graphs here. Let's go up to 3, and then maybe we'll go down to -3, -2 here, 4, 5, 6, 7, 8. Okay, so if I want to graph the line 3, this line here, the very first piece would be y equals 3 if x is less than or equal to -2. So y equals 3 is a horizontal line at 3, starting in an x value of 2. And so that line at 3 would head off to the left, but not to the right. The next piece, we would have y equals 1 minus x if we are between -2 and 0, including 0. I would choose to rewrite this as -x plus 1 because I just find it easier to graph that way. So this would have a y-intercept of 1. We include that point when x is 0, and we have a slope of -1. So the problem is that we're going to overlap our blue point with this line, but it does not include that point on the purple line there. So it's like the blue filled in dot point are going to overlap with our open purple point. And the last piece is y equals x squared if x is greater than 0. So our very first value we're going to include is just past 0. At 0, we're going to have an open circle. We get to include our point at 1, 1 and at 2, 4, and we know that this is a parabola. Okay, at 3, 9, we can include that point too if we want. Okay, so that would be our piecewise. So break it down piece by piece. Remember, the do not includes should be an open point, a hole, and any other includes you can fill in those points. Last piece of review for today is absolute value functions. So just a reminder, your absolute value equals itself if the stuff inside was already positive, and the absolute value equals the negative of itself if it was negative. So what this means really is, for example, absolute value of 5 is equal to 5. Absolute value of -5 is equal to 5 as well. But this also is written as absolute value of -5 is negative -5, which is +5. So this is where this negative a part comes from here. Okay. So what we need to figure out is the stuff in the absolute value positive or not? Okay. 8 minus root 2. Root 2 is about 1.4. So 8 minus root 2 is positive. So this is just going to equal itself. Okay. Pi minus 5, this is about 3.1 minus 5. This is negative. So this is going to have to equal the negative of itself. Okay. Or you can write it as negative pi plus 5. Okay. So this here, we're in this situation, a is greater than or equal to 0. And this here, we're in this situation, a is less than 0. Now, the next one, if you don't actually have numbers, you're going to have to write cases for yourself. Okay, so here, case 1 is that the absolute value of x plus 4 is equal to itself if x is greater than or equal to negative 4. Okay, so then you would have x plus 4 minus x is equal to x plus 4 minus x, which would be equal to 4 if x is greater than or equal to negative 4. Case 2, your absolute value, x plus 4, is equal to the negative of itself if x is less than negative 4. Okay? So this means that x plus 4 minus x would be equal to negative x plus 4 minus x, or negative x minus 4 minus x, or negative 2x minus 4 if x is less than negative 4. Okay, and that's it for today.